Hey guys, welcome back to the Dynamics video series. This is the second video on pulleys. This one is going to be talking about pulleys including free body diagrams. So let's go ahead and get started. This question states, I think this is actually an old exam problem. 6.71 kilogram frame A is welded to the floor so it doesn't move, right? So our frame is not moving, that big L shape. There's a 10 kilogram block, is smooth, so there's no friction. So we're not going to be dealing with friction on block B. And then what is the acceleration? This is what we're looking for of the 20 kilogram block C. So our goal here is we're looking for the acceleration of C. All right, so this is what we're looking for. All right, so let's start thinking. So again, even though this video says that we're going to be needing free body diagrams for these problems, how would you know that if I didn't tell you explicitly? So we do have to do a couple things. We have to figure out, do we need a free body diagram? Is it a dead giveaway? So remember, a dead giveaway is if it's asking you for a force, or if it's like, what's the tension in the rope, something like that. What's the normal force of friction? If it's asking for a force, that's a dead giveaway that you're going to need a free body diagram. It's not asking for that in this case. In this case, we're talking about the acceleration of block C. So it's not exactly a dead giveaway. But then we have to count our degrees of freedom. So our degrees of freedom. So let's see how many we have. So if you imagine that you can hold, I don't know, block C in place, right? Can anything else move, or is anything else gonna move, right? If block C is held in place and it's that rope is connecting block B and C, block B is also not gonna move. If you can also imagine that block B is held in place, obviously block C is not gonna move up or down if block B is not allowing it. So those two have to be moving in some type of tandem. So we have a 1 degree of freedom here, right? Because if you stop one of these from moving, the other one can't move either. So what do that mean when we have 1 degree of freedom? If we have 1 degree of freedom, that means if we're given one acceleration, we can find another acceleration. Or if we're given one velocity, we can find another velocity in this system. That's not the case. In this case, we're actually only given the masses of these two blocks, right? So we're not actually given an acceleration, and we're looking for an acceleration. Actually, this is the mass of the frame. That's not going to be as important. So we're looking for an acceleration given no acceleration, so that's a dead giveaway. Not a dead giveaway, but that's a tell that we're going to need a free body diagram. So in this one, we're going to draw free body diagrams. So let's start. So I'm going to draw the free body diagram first of body B. So free body diagram of B. All right, let's just draw right here. So I'll just make it a block. So this block is going to be block B, right? I won't label it just so I can draw the forces. And then we got to see what type of forces are acting on block B. So block B is going to be moving. We got to first look at the contactless forces, or the action at a distance forces. In this case, and in almost every dynamics problem, it's always going to be gravity. So we do have gravity acting on this block, and that's mg. We also do have a normal force acting on the block, right? And that is going to be the normal force, right? Perpendicular to the floor in this case, and since we're on a level surface, it's going to be just straight up. The question does tell us that it's smooth and there's no friction, so we're not going to have to draw a friction force, so that gets rid of a possible force. And then now we're going to look at our contact force of the cord, right? So the cord is pulling to the right, or not to the right, to the left on this thing, right? And that's just going to be the tension in that rope that we're talking about, right? So this is our free body diagram for body B. And now we can do a summation of forces. So get into the habit. Every time you draw a free body diagram, just start summing the forces. Easy way to sum this one is in x and y components, right? So x is going to the right, y is going up for the positive directions. So let's sum in the x first, or we can just do y first just to show something. So the sum of the forces in the y. So n is positive, it's going up, minus the whole component of mg is going to be equal to our, what's it called, mass times our acceleration of block B in the y. If you notice, as block B moves, it's not going to be jumping off this frame, right? So there's actually going to be no acceleration in the y component for block B. So what this becomes actually is n minus mg equals 0, because if we have 0 acceleration, 0 times mass is still 0. And then we can get that, oh sorry, this is the mass of B. I'm going to label that more explicitly. N equals mg. it doesn't help us very much, this one, or MBG, I should write. But it's important that you practice that. So now let's sum forces in the X, right? In the X, there's only one force, and it's just T. It's going to be negative T, right? Because it's acting left of our positive axis. And that's just going to be equal to our mass times our acceleration of B in the X direction. Right? So that's the free body diagram of B. I'm going to draw the free body diagram of C up here, just so I can have space to work with down there. So free body diagram of C. Let me draw this block as best as I can. So it's like something like this. A little taller, skinnier. There you go. So this is block C. So let's draw all the forces. So first, always there's gravity. So we're going to have gravity pointing downwards. And that's going to be the mass of C times G. Let me go back and label this one mass of B, just so we know. And then there's no other contacts besides that tension force. So there's going to be a tension going up. And that's the same tension that exists in block B. So same T. And now we can do summation of forces. So if you notice, there's no forces acting in the X direction. So we can just ignore that. So the forces in the Y direction is what we'll be summing. And then that will get us that positive T minus M, M of CG equals our mass of C times our acceleration of C in the Y, right? Which is the whole component of C. I ran out of room a little bit. I'm going to rewrite that just for clarity. So I got from this that T minus MC times G equals mass of C times the acceleration of C, right? C is only accelerating in the up and down direction, so I'm just going to label it as AC. Okay, so we have two equations. We can kind of link them using T. Let's see how many variables we have. So we want to find AC. We want to find tension. We want to find also AB is unknown, and tension's unknown over here. So in total, we have one tension, one AB, one AC. So we have three variables and two equations. So right now, this problem is algebraically insufficient. We can't solve it using algebra quite yet. So that tells us we're going to need to relate them in some other way, which, as you guys know, is the rope equation. So let's do our rope equation, right? So if you remember from the last video, we're going to get the length of the rope. Right? We only have one rope in this case, so this one's a little easier. So this just equals. So let's find the length. First thing we got to figure out is what's moving. So C is moving and B is moving, and those things are labeled. And then nothing else that's moving is labeled besides A. We can just get rid of A. A doesn't really matter. So then we can figure out these distances. So let's create this arbitrary distances for C. So this distance from this fixed point up here to C, we can call it YC. And then this arbitrary distance, right, we can call it YB, or XB, better. Okay. So let's write our length for these equations. So this little portion is going to be XB, right, because it's just that distance from that fixed point to B. So XB plus, and then we can do this top part. So this top part, you'll notice, is XB, a portion of it, right? But let's see what the total thing is, right? So if we want to say from this fixed point over here to this fixed point, it's going to be some distance, and these two are fixed points, so this is going to be a constant distance. So this top distance is just going to be this constant, right? Wait, what's up here? It's just gonna be this. Oh yeah. So this XB, this top bar is always gonna be constant, right? So it's never gonna change. So it's not really gonna affect it very much. So we're just gonna label it as C, right? Because it's a constant. And then now we're gonna look at this vertical portion of rope that we're talking about next to this pulley. This vertical portion is just gonna be YC. So this pulley is very simple, which is helpful for us. So plus YC, and then that's gonna be our entire rope. So now, like we did before, we can take a time derivative of our rope, and that's going to give us the change in these XB and YC values. So XB dot, that C disappears because it's a derivative, and it's a constant, and then plus YC dot. Perfect. And then we know that the length is of a constant, the rope is of a constant length, right? Incompressible and doesn't extend. So we know that's going to end up equaling 0 because there's not changing in length. That's what that LR dot term means. And then we can just rearrange this equation. And then we get that XB dot equals YC dot. Or negative YC dot. Yeah. Because I had to subtract it. Negative YC dot. Perfect. And now we just got to figure out if those relate to our axes in a proper way. So based on my free body diagrams, I drew the positive direction as Y for going up, and then the positive X direction as going to the right. So I'm got to make sure to keep that convention when I talk about these changes in lengths. So as XB increases, right, or as it goes this way, is B going to the right or to the left, right? If XB is increasing, then B is going to the right, because it's the distance from this point, right? So those two line up exactly. So XB dot is the same thing as VB. Perfect. So we can plug that in for VB. But first VC. So we got to notice for this one, it's a little different, right? So as this distance increases, right, this distance, as it gets bigger, C has to be going down. And if C is going down, right, then we attributed that as a negative value, right? So actually for this one, YC dot is equal to negative VC, or the negative velocity of C, right? And so let's plug both of these into our equation. So if we plug this in, oh, actually, I skipped a step, and because I didn't realize for a second, but we're actually working with acceleration, so let's go back just 1 second. I'm going to erase this really quick. It's the same thing, but we're actually working with acceleration, not velocity, right? So what you can do is after you do this first derivative, it's an extra step, and it's good to stay explicit, so good job if you caught it. We can actually, if we're working with acceleration, we need the second time derivative of the length, right? Which is still going to be equal to 0, but it just adds a second dot on top, which it relates to acceleration, right? Because the derivative of velocity is acceleration. So xb double dot plus yc double dot. It didn't change much with our math. It's just important to recall that we're working with acceleration, not velocity, right? Because we're talking about forces in this case. Okay, so it's the same conclusion we came here, where xb is actually the acceleration of b, or x double dot xb. And then yc double dot is just the acceleration, or sorry, the negative acceleration of c from what we determined based on our axes, right? So we can rewrite it again. So this becomes xb double dot equals the negative yc double dot, which becomes, again, based on what we just said, vb equals vc. Oh, not v. I keep putting v. AB equals, and then it's a negative of a negative AC, right? So this just becomes that AB is equivalent to AC. All right, perfect. So let's do it now. Okay. So we have a couple equations, right? We have 3 equations and 3 total unknowns. So we can actually start solving. I'm going to move stuff around so we can solve algebraically. I haven't solved it yet myself, so that's a good chance to do it together. So let's start, just write our equations out. We know that negative t equals, and then we're just writing our mass. So this is the mass of B. Mass B was 10 times AB, right? So that's our first equation. And then our second equation was that, let's see what's up here, T minus, and our mass of C is 20, minus 20 times 9.8 is equal to, and then our mass again, which is 20, times the acceleration of C. Okay, and then our last third equation is that AB equals AC. All right, so we can kind of just replace AB or AC in these equations. So I want to solve for AC, so let's go ahead and replace AB with AC, right? So I'm going to turn this equation into negative t equals 10 AC. Right? And now I have two equations, so I have this one and this one for t and AC, and we can go ahead and solve. So let's figure out what t is based on this first equation. So from this first equation, if we want to get t, we can get that t, we just move the negative sign over. It's just the same as t equals negative 10 AC. And then we can plug that value in for the t on this bottom equation. So let's do that down here. So we have negative 10 AC minus 20 times 9.8 equals 20 AC. And then if we solve for AC, we're going to move the 10 over. So this equation, I'm running out of room, so I'm just going to move it up here. 30 AC, right? I have to do the algebra, equals negative, calculator says 196. Okay, 196. And then finally, we're going to get that AC equals negative 196 divided by 30, or just 6 or negative 6, keep the negative sign, 6.53, and the unit for acceleration is meters per second squared. So that's going to be our answer for this first problem. Okay, guys, this is going to be the second problem for the free body diagram part. So again, how do we determine we need a free body diagram? Essentially, it's going to be not a dead giveaway because it's not asking for a tension. Wait, let me read the problem first. So block A is 20 kilograms, block 2 is 30. The angle is 36.9 degrees, and there's no friction. And then what is the acceleration of C? Right. So it's not a dead giveaway. Again, the question didn't ask for anything like a tension, anything like a friction force, anything like a normal force. So no free body diagram needed there yet. And then we got to count our degrees of freedom. So that's the next step. So it wants to find an acceleration, right? And so we should be given at least one acceleration, right? If we don't need a free body diagram. The problem doesn't give us any accelerations. It's only giving us weights in degrees. So that's a good sign that we're probably going to need a free body diagram in order to solve for this acceleration because we're not given anything to solve with. So let's go ahead and do it. So let's start drawing free body diagrams. I'm going to draw it first of C. So let's do FBD of C. That's going to be up here. A little more space of C. And it's just a vertical block or a vertical oriented block. And there's a couple things acting on it. So we have this force, right? This contact at a distance force, or not contact at a distance, force at a distance, which is gravity, very common. And that's just going to be the magnitude of mass of C times G, right? We have something else. We have the force that this pulley is exerting up on this block. Now, is that force just the tension of the rope? No, right? We can actually, what we can do is treat the free body diagram of C as this entire portion, right? Because they will be moving together, right? So if that's the free body diagram of C, and that's what this block up here as U represents, then we actually have two ropes pulling up on it, each with the same tension, right? Because if a rope is wrapped around something, the entire rope is going to have the same tension. So actually, this top force is going to be 2 tension, or 2T, right? And that's our free body diagram. Let's sum forces. So the sum of the forces so far, there's only forces in the y, so that's what we'll do. Let's establish our axis. So let's say going up is positive and going to the right is positive. So our in the y, we have positive 2t minus mcg, and that's going to be equal to our mass of C, just F equals ma, times our acceleration of C. Okay, so that's the first part. Let's do our second free body diagram. So FBD of B. Okay. And then we'll draw it. It looks kind of slanted, so I'll do my best to draw it kind of slanted. That's probably as good as it's going to get. Is our action at a distance forces first. So again, this is just gravity. So this is pulling down with a force of mb, or is this B? Oh, this is block A, not B. So let me get this
out of the way, just so my labels are correct. M free body diagram of A, and this is the mass of A times G. I want to write that red. I like writing all my forces in red. MAG. Right. We do have more forces. We have contact forces. So we do have this rope attached over here at this side. So that's just going to be a tension going this way. All right, I'll draw it on the dot to make it feel better. So that's a tension going this way. And then we have one more, which is the normal force, right? Because it's contacted at this surface. So there's a normal force pushing up on it perpendicular to the surface. So it's going to be just perpendicular this way. And that is going to be N, right? Okay, so let's make this a little easier on ourselves by drawing these lines and then writing our angle in. So these two form a 90-degree angle, right? Because they're perpendicular. And then MAG is in some type of component. So let's see what these angles are. So we know that this angle over here is 36.9, right? And so if gravity is acting downward on it, gravity is going to be this angle here. Let me draw it with this color. So this angle right here is 30, it's called 6.9. Perfect. Degrees. Okay, so let's sum our forces. So sum of the forces in the x direction. We'll just treat the tension as the x, so write this positive, and this upwards as the y. Just so that these two are lined up pretty easily, and we can just worry about the cosine and sine of our gravity in a second. So in the x direction, we have a positive tension, so plus t. And then gravity isn't also a component of this, but it's negative because it's going in the reverse direction. So negative m a g. And then is this going to be sine or cosine? What do you guys think? So if this angle, right, is right here, then the angle opposite of it, or this one, is the sine, or the, what's it called, component. And then this one is the cosine. You're thinking of it like a what's the word? Like a, just a person you're next to, co-worker maybe. That's the co. Is going to be next to the angle, and the sine is opposite. So which one of these line up with the x-axis? That's going to be the sine component. So this is going to be sine of this angle. So sine of 36.9 degrees. Right? And this is equal to our acceleration of, well, the mass first. The mass of A times the acceleration of A in this x component. Okay. And then let's do the y component. So F in the y. If we notice, we only have no tension in the y. We have a normal force though. So we have plus n, and that's going to equal to, not equal to, that's going to be minus because our gravity is acting against the normal direction, or against the y, positive y direction. Just again, ma times g. And then since we said in the x direction it was sine, in the y direction it's going to be cosine of 36.9. Right? And then we can keep going. So this becomes our mass of A times our acceleration of A in the y. And then if you notice the trend with these types of problems, there actually is no acceleration up or down in the y because this block is stuck on that path. So this whole side actually just becomes a big 0. Perfect. So let's see, can we solve this? Let's count our variables. So we don't know AC. We don't know tension. We don't know AX, acceleration of A in the X, and then that is it. Well, we also don't know the normal force. We do know the normal force because you can use it to solve for it. But this equation doesn't have any other variables we need. So we really only have these two equations, this one and this one, and we have 3 variables to solve for. So that's not sufficient. So we need to do a rope equation for sure. So let's do our rope equation. So let's figure out the lengths. I'm going to erase some of my drawings I put on here just so that I can talk more effectively about the ropes. So let's get a distance of this rope, right? So the length of the rope, right, or this rope equation, write it better, not the highlighter. The length of this rope is going to be equal to, and then let's get the length. So bring my highlighter out. what's this first distance, right? We can just say it's something like from this fixed point down to the A, or x of A, right? Perfect. And then let's get the second distance. So this is going to be first xa. And then let's get the second distance. If you notice, these two are always going to be the same. Where's my highlighter? These two are always going to be the same, right? Because C is on the bottom of them, just pulling them both. So these two are actually both just going to be, it's called YC. Okay, so we have 2YC, so plus 2YC, and we have no constants for this one, so that's easy. Now we're working with acceleration, so what we're going to do is we're going to take the second time derivative of both of these, right? And that's going to be just adding the double dots, xa double dot plus 2, and then yc double dot. Straightforward enough. Let's continue on. So now we have to change these equations into something we can use. So these correlate to our acceleration, but they're not exactly the same as our acceleration. So actually, let's look at our axis and then figure out if these are in the positive or negative direction. So as yc gets bigger, right? As yc gets bigger, is the y as the for the c free body diagram, is that a positive or a negative change in or direction for velocity or acceleration? As yc gets bigger, right, this thing is going down, right? So if it's accelerating more, if yc is the change in the change is getting more, then this thing is in the negative direction, right? So we actually figure out that yc double dot is equal to negative acceleration of c. And then we can do the same thing for the a. So also in our a-axis, we notice that this x-axis increases in the opposite direction that our xa over here would increase. So it's the same logic that xa double dot is just this a acceleration, negative acceleration of a. Okay, so we can rewrite this equation. So the negative acceleration of a is minus, this is minus? Yes, minus 2 times the acceleration of c equals 0, right? And then we can confirm that the acceleration of a equals minus 2 acceleration of c, right? So that's our equation. Since we're solving for the acceleration of c, I'm actually going to rewrite that. Actually, no, that's fine. We're solving for the acceleration of c, so I'm actually going to be using this to plug into these equations. So let's say I want to get rid of this acceleration of x that I was talking about for this equation. I'm going to go ahead and rewrite this equation, but I'm going to sub that term out for my AC term. So I'm running a bit out of space, but I'll write it down here in the bottom right or bottom left. So I'm going to write that second equation, so this one right here, so 2 and 1. Let's plug it in. So T minus, and then MA is based on the given information, 20, times gravity, which we're 9.8 since we're working with SI units, and then times the sine of 36.9 equals the mass of A again, which is 20, and then times the acceleration of A, which we determined was negative 2 AC. And then let's bring this other equation down. So we know that 2T minus the mass of C is 30. Times gravity, 9.8. 9.8, and then this one is going to be equal to our mass of C, which again was 30, times our acceleration of C. Okay, so you have two equations, two variables. Let me pull up a calculator and solve the algebra. Okay, so I use an algebra solver. If you're on an exam, you have to do the algebra yourself, or you can use the Mathematica software, which is what I used. But I got that AC is equivalent to, and let me make sure I'm copying this correctly, negative 0.402. ish. All right. Meters per second squared. So what does that mean? If you're asking for like a speed or a rate in a direction, you can get this. So that becomes that 0.402 meters per second squared. In what direction? Down. Okay. Zooming out now, I see I wrote it a little small, but I hope you guys can see it. So that's going to be our answer for this problem. Feel free to reach out if you guys have any questions. Just make sure when you're solving these, you identify if you need a free body diagram or not. Drawing the free body diagram correctly, making sure you're summing your forces correctly. That's what we've been doing for this past semester. And then finally, the addition of these rope equations, making sure you're creating the right rope equation is just the key to success. But that's going to be it for the video. See you.